All right, welcome back, guys, to Learning as a Hobby. This video is for the solutions to Section 1.5 in Taylor's Classical Mechanics, which I just posted uh, the section summary for on the channel, so you can check that out if you haven't seen that yet. Let me bring up the solutions to the problems on the board here. All right, there's only a few problems in this section, and I left out two of them because they deal with you have to know something about electromagnetism or electrodynamics or whatever. You have to know about that to do those problems, and I don't. So he says you can omit those and come back to them after you've had a class on electromagnetism. So I'll do that when after I learn about it. I'll learn about that, which we'll do, after we get through Taylor's book. Um, so I just did all the other problems from the section, which I think there was only like 5 or 6 of them or something. So we'll just go through them one at a time. The first two problems are very similar to each other. So let me just read 128 and then I did them both at the same time, just because, like I said, they're very similar. Just one is the case n equals 3 and one is the case n equals 4. But let me read the instructions here. Go over the steps from equation 1.25 and to 1.29 in the proof of the conservation of momentum, but treat the case that n equals 3 and write out all the summations explicitly to be sure you understand the various manipulations. And I should actually make a note here. I realized afterward that when I was talking about the equivalence of Newton's law, third law, and the law of conservation um, of momentum, what we proved in the section was that the law of conservation of momentum follows from Newton's third law, not the converse of that. But we will do that in the exercises. So I just wanted to mention that because just so that people don't think that that proof was for the equivalence, because it wasn't. It was that one follows from the other. So anyway, that's question 128. So in other words, they want us to show basically that for n equal a 3-particle system, n equals 3, and then they want you to do the same thing in question 129 for a 4-particle system. So exactly the same problem, just for n equals 4, right? So I did them both at the same time. So this is for n equals 3 and this is for n equals 4. So I'll just guide you through them. All right, for a 3-particle system, the total forces on 3 particles are written here. The total force on particle 1 is F1, which is given by F12 plus F13 plus the external force F1. And that's the same thing as the time derivative of its momentum, and same thing for the other 2 particles. Okay. The total momentum of the 3-particle system is the sum of the 3 momentums. So P1 plus P2 plus P3 gives you P, which is the total momentum. And if you take the time derivative of that, you get the sum of the time derivatives of each individual particle, which I have written out here in terms of the forces, right? And then notice that if you rearrange things here, you get F12 plus F21 plus F13 plus F31, etc. All of those cancel out by Newton's third law, and you're left with the sum of the external forces on each of the particles, which is the total external force. And of course, if the external force is 0, then the time derivative of the total momentum is 0, which means that the total momentum is constant. Right, and then I did a similar thing for n equals 4. I used a little bit of shorthand notation just so I don't have to write all the subscripted terms out here, but it's exactly the same proof. Here I'm showing that all of these similar things cancel. F12 cancels with F21, F13 cancels with F31, F14 cancels with F41 down here, F24 cancels with F42, and F34 cancels with F43, and you're left with just the sum of the 4 external forces. And of course, if that's 0, then the time rate of change of the total momentum is 0. Again, that implies that the total momentum is constant. So that's 128, 129. All right. Let me read out question 130. which says conservation laws, such as conservation of momentum, often give a surprising amount of information about the possible outcome of an experiment. Here is perhaps the simplest example. Two objects of masses m1 and m2 are subject to no external forces. Object 1 is traveling with velocity v when it collides with stationary object 2. The two objects stick together and move off with common velocity v prime. Use conservation of momentum to find v prime in terms of v, m1, and m2. So that's what I did down here. All right, using conservation of momentum, the total momentum of the system is some constant c, which is equal to these two expressions here. So m1v plus m2 times 0, because the second particle is has zero velocity. It's not moving, right? It's stationary. So this side simplifies to m1v. And like I said, that's constant by the law of conservation of momentum. But once they stick together, the total momentum of the system has to stay constant. So that would be equal to m1 plus m2, because that's the new mass, right? Times the new velocity v prime. So this has to be equal to that. Setting them equal to each other gives us this. And then you could just solve for v prime by dividing by the sum of the scalars m1 plus m2. So the new velocity v prime is m1 over m1 plus m2 times the original velocity v, right? So it slows down, which should make sense intuitively. Okay, that's 130. Let's see, 131 says in section 1.5, we proved that Newton's third law implies the conservation of momentum. Prove the converse, that if the law of conservation of momentum applies to every possible group of particles, then the interparticle forces must obey the third law, right? And he gives a hint on how to do this. However many particles your system contains, you can focus your attention on just two of them. Call them 1 and 2. The law of conservation of momentum says that if there are no external forces on this pair of particles, then the total momentum must be constant. Use this to prove that F12 equals negative F21. All right. I guess that there's an assumption in there that it doesn't matter what the size of the system is. You can just focus on two of them. But I guess experimentally that's been verified to be true, so we can take it as a fact, which is what he's telling us to do here. So, all right, so here's the proof. Assume the law of conservation of momentum applies to every group of particles, then it holds for n equals 2, obviously, right? Because n equals 2 is a group of particles. Then if the external force is 0 for both of the particles, then the time rate of change of the total momentum is 0, which is equal to the sum of the time rate of change of each of the individual momentums, which is equal to F12 plus F21. And then just subtracting F21 from both sides shows that F12 has to be negative F21, and that's it. So that completes the equivalence of Newton's third law with the law of conservation of momentum. All right. And I think this was the last problem I did. So prove that that in the absence of external forces, the total angular momentum, which is defined this way, and actually this should have a vector arrow on top as well. L is a vector quantity. L is equal to summation over alpha, R alpha, cross product with P alpha. So the P alpha is the momentum on particle alpha, and you're dotting that with I guess this would be the radius away from the point of rotation, I guess. I think that's what that means. But just using the definition here, we can prove this of an n particle system. So prove that the angular momentum of an n particle system is conserved. He also gives you a hint here. He says you need to mimic the argument from 1.25 to 1.29. In this case, you need more than Newton's third law. However, in addition, you need to assume that the interparticle forces are central. That is, F alpha beta acts along the line joining alpha and beta. A full discussion of angular momentum is given in chapter 3. All right. All right. So here's here's the proof. So just using the definition he gave us, L is equal to the sum of those cross products. If you take the time derivative of L, you get that sum of that more complicated looking formula, which comes from it's a formula for differentiating cross products. It's a type of product rule. He asked us to derive this in, I think it was like section 1.2, I think it was. And if you recall, I actually skipped over all those formulas because I said, well, do end up doing them in Schifrin at some point anyway. But I'm just using that formula here. So the derivative of the cross product Ri cross Pi is the time derivative of Ri cross product with Pi plus Ri cross product with the time derivative of Pi. And then I'm just simplifying some things here. So that's equal to the time derivative of Ri cross Mi Ki time derivative Ri. So that's just from the definition of Pi, that the momentum of particle I. It's the mass times the velocity. This part here is the velocity of that particle at time t. Okay, and plus that I just distributed the summation operator here, plus Ri cross the summation Fji, where j is not I, plus the external forces on the ith particle. So in other words, I'm just expanding the time derivative of Pi. So that gives you the sum here. Okay, and then simplifying a bit more. This, if you look, this cross product, because the forces are what did he say? They're central, right? That you get this for the velocity here. The cross product of these is 0. So you end up with just this cross product, the sum of these cross products here, plus this, and then you can use Newton's third law to show that this sum is 0 because all of these are 0. And when you take the cross product of anything with the 0 vector, you get 0. You get the 0 vector from that. So plus this Ri cross the sum of the I going from 1 to n of Ri cross Fi external. And this simplifies to this because, like I said, this is 0. And since there are no external forces, each of the external forces on the individual products, sorry, the external forces on each of the individual particles is 0 for, so for I going from 1 to n. Therefore, this cross product here is equal to the 0 vector. That's dl dt. So that shows that the angular momentum is constant, right? And that's basically it. It's very similar to the proofs for the other cases here for the conservation of momentum. But you have to know a little bit about cross products, and like he said, you also have to know that the forces are central. And that's it. Those are the problems I did for this section. Like I said, let me just stop the screen share for a second. There's actually only 2 other problems in that section, but like I said, you have to know something about electricity and magnetism to do those problems. So I skipped those, and we'll move on to section 1.6 from here. And we'll continue on with the rest of the books and everything when I get a chance. If you didn't watch the most recent video I posted, I have a kind of a busy schedule at work right now, so it's going to be the videos that I post it's going to be a little bit slower in my schedule, the posting schedule, just because of that. So, but I am working on these all the time. It's just taking me longer than it was before. So, thanks for watching, guys. Remember to subscribe if you like watching this content. Like the video if you feel like you're getting something out of this, and I'll see you guys in the next one. All right, goodbye for now.